Guys, my name is Benjamin Bory and I am an engineer here at Spin Ion Technologies, and today I will introduce you to the Hall effect measurement. So most of you are probably aware of the common Hall effect that happens in non-magnetic metals. So in the presence of charges moving whilst the magnetic field is present. What we want to talk today about is the anomalous Hall effect, which in this case is present in ferromagnetic materials. So this effect, this anomalous Hall effect, comes from various contributions. They're usually assembled in two different portions. First, an internal contribution that comes from the band structure of the material, and an external contribution that comes from scattering upon defects. This anomalous Hall effect can be very, very large. It can be 10 times larger than the conventional Hall effect. And it has the advantage that it will follow the direction of the magnetization. So for example, if you have magnetization pointing up, then you might have a low conductance. And if you have magnetization pointing down, then you might have a higher conductance. So it's interesting because then you can follow the switching of magnetization and anisotropies, and basically what you want to do with your ferromagnetic material is acquire hysteresis loops, for example, as you could acquire for VSM measurements or Kerr setups. The advantage of this setup is you can measure very tiny devices up to 100 nanometer. So let's get into it. So this is the Hall effect measurement setup up close. So what we have here is a sample that is pasted on a PCB board. The sample is also wire bonded on the four corners, essentially to be able to apply an electric current to put charges in motion in one diagonal of the sample, and in the other diagonal of the sample we will collect the anomalous Hall effect contribution. So here the sample is placed in between two coils, and the sample is mounted on a sample holder that can rotate in different configurations. So that what we can measure is, for example, an in-plane configuration where the applied magnetic field provided by the coils is inside the plane of the sample, and in an out-of-plane configuration where the applied field provided from the coils is normal to the surface of the sample. So now the coils, they are connected to a KEPCO power supply that will supply the power to make the magnetic field. And the sample is connected to a Keithley here that provides the current in one diagonal of the sample, and we collect the voltage in the other diagonal. So in the conventional measurement, how does it work? What we want to measure, remember, is an hysteresis loop, right? So what we do is we take the sample, we apply a constant current in one diagonal, then we constantly monitor the voltage in the other diagonal, and then we start increasing the applied field in one direction, so in the up direction, so that we take the magnetization outside of the plane, for example. Then we let the applied field go back to zero, and then we push the applied field in the other direction, the magnetization follows, and then we come back to a positive field. And there you have it, you have the full hysteresis loops. So from that you can extract several informations: an easy axis, a hard axis, coercivity, anisotropy fields, and switching fields, for example. So this is it. This is the Hall effect setup.